Why, hello there. Today we are going to look at a very interesting or slightly different photoelectric effect graph. Okay, we're going to focus this video specifically on the relationship between wavelength and the photoelectric effect. All right, there will be other example videos relating maximum kinetic energy, frequency, etc., with the photoelectric effect. So make sure you check them out as well. It will be included in the playlist, either in the playlist or wherever you see this. It should be in the list. Okay, anyway, let's begin. So this is from Winter 11 paper 43, and it says that an explanation of the photoelectric effect includes the term photon energy and work function. Okay, sure. I explain what is meant by a photon and work function energy. Okay, so after doing many years of past year question, because it's part of my job, she's kind of part of yours as well right now if you want the A, I know how to write a 3-mark explanation. So I will story you the 3-mark explanation, and you don't know where the marks are, so might as well just write the whole thing. It's not too long. So a photon here is a light particle. We call it a particle because the energy is concentrated in a ball. Okay, so we're going to call this a quantum. Don't want to use quantum for quantum physics. You can maybe call this a packet, okay, of energy of electromagnetic radiation. All right, so if you're wondering where is the last mark, right? First 1 mark is when you mention quantum or packet of energy. The other mark, second mark, is when you say this is electromagnetic radiation, so it can be all the way from radio wave to gamma. Okay, and the final one, the final mark will be where the energy of a photon E is equal to the Planck's constant multiplied by frequency of the EM wave. Okay, so this one is that anomalous year where they ask a 3-mark explanation, so make sure you cover all 3 marks. All right. Okay, so for this one, it's only 2 marks, so it's the first 2 points. This one is the add-on. Work function energy. So when you see work function, this is the minimum energy. Okay, so the minimum, look at the slew rate of, there we go, change color. Minimum energy, be a bit specific, of incident photon, okay, to cause or to produce photoelectron emission. This is good enough, but I just want to complete it from a metal surface. So you should know by now different metal will have different work function energy. Certain metals are more electronegative, so they are more reactive, so they will release the electrons more. Okay, so let's look at B. An experiment to investigate the photoelectric effect. A student measures the wavelength of light incident on the metal surface. We're going to measure lambda and the maximum kinetic energy, your Emax of the emitted photon. And we're going to look at Emax and 1 over lambda in this graph. So always check the axis, remember in the video, okay? The theory video, we have already reminded you to check the axis. This is 1 over lambda. Don't forget there's a prefix hiding here, okay? Take note of the prefix. And then this is your maximum kinetic energy. Okay, slightly anomalous graph, but we're not worried. Let us continue and see what the question wants first. Okay, so it says here that the work function energy of the metal surface is phi. Okay, state an equation in terms of lambda, phi, and Emax to represent the conservation of energy of the photoelectric effect. Explain any other symbols you used. Okay, fine, sure. So I will say that the energy of photon, because that is the one that gives the metal, that is incident on the metal surface and give the metal energy, the electron energy, I guess you could draw. So this is metal, and we have some electrons chilling under the surface, some a bit deeper, some even deeper. Now it looks like a binomial triangle, so I'm just gonna draw a lot of electrons, okay? And then maybe we can incident some purple light, some beautiful purple light of high frequency. I don't know what light this is. So these are your wave packet, or I guess you could draw them in particle format lah. Anything lah. So this is the energy of the photon. And then the electron will be ejected out. If let's say you are shooting this electron, okay, so let's say there's another. Okay, so the electron will be ejected out. So the ejection will be work function. Okay, and once the electron is outside here, it will have its kinetic energy. So if you took the least amount of energy to escape, you will have the most amount of kinetic energy left behind. So the energy of a photon here will be equal to the work function plus Emax. But you see there's no lambda. Okay, so here it's probably good to remember that the work function energy E is equal to HF, which is also equal to, photon energy E equal to HF, photon energy HC over lambda. So I guess this one you can substitute HC over lambda is equal to work function plus Emax for your first mark. But they say explain any other symbol used for. So if I want to explain the symbol, I will just say where H is the Planck's constant, and C is the speed of light. I want to be very specific, this is in vacuum lah. But don't worry, in air, in vacuum, the speed of light is small, it's very close. Anyway, using this equation and the graph, determine the work function energy of the metal surface and a value for the Planck's constant. So you cannot go and use Planck constant in part 1 of the calculation. In fact, they won't allow marks. I think they will only give you like 2 out of 5 marks because this entire part is 5 marks, 2 plus 3. So please try to read the whole question and understand that if they want you to calculate the Planck constant here, even though you know you can flip to the front of the paper and find the value of Planck constant, you are not allowed to use it until you unlock this level, until you find the Planck constant, and then the question also finished already. So okay, never mind. So let's take the equation. They say take the equation. Okay, I'll take the equation. HC over lambda is work function plus Emax. Now I go and stare at the graph a bit. I need some inspiration. So instead of staring at the wave like Pablo, I go stare at my graph. Okay, my y-axis is 1 over lambda. This means this one should look like 1 over lambda. Y equal to mx plus c. So I must try to make the subject of the equation the same as the y-axis, which is 1 over lambda. So I'm going to put this one as 1 over lambda. Hiya, what to do with the hc? Divide by hc lor. So here you will have work function over hc plus Emax over hc. Okay, we think a bit. Miss, our graph is, this one is the y-axis. So I'm just going to write down here for our brains to brain. This is y. Okay, what's your x-axis? X-axis is Emax. I'm just going to highlight the Emax here. We need to bring it to the front. So Emax is here. Okay. And what is your gradient? 1 over hc. Okay. Plus, this whole thing, work function over hc is your y-intercept. So I'm going to compare this with the general equation of a straight line. Oh, this is not y, sorry. This is 1 over lambda. Okay, I'm going to compare this with the general equation of a straight line. And this is my y. Y is equal to mx plus c. So Emax is your x-axis. Miss, cannot leh. You see, if I want to find the work function energy, I use the y-intercept. But if I use the y-intercept, I need to use the Planck constant, so I'm stuck. Okay, don't worry. You cannot use the y-intercept. Can you use the x-intercept? Oh yeah, this question cheat your feelings. Cannot use y-intercept. So normally when you have a graph, right, you can either find gradient, x-intercept, or y-intercept. Because physics graph all straight lines. Straight line, bro. We like straight lines. Okay. Normally, I hope that you are in a safe space where you can love whoever you want. But for physics, we only like straight graphs. I mean, most of the time. Okay, so anyway, after that rambling here, we cannot use the properties of the graph. So we need to try plan B. We will let, so you want to find the x-intercept. The y-intercept does not work because this y-intercept, we have the Planck constant here. So we're going to try to find the x-intercept. So at the x-intercept, let's say I extrapolate the line or the graph. Okay, so I have extrapolated to find the intersection with the x-axis. So you will notice that at the x-axis, the y-axis is 0. So you can let 1 over lambda be 0. Let's see if that helps. I don't know, because that's the last method, right? So I'm going to let 1 over lambda be 0. Then this is for us to find the x-intercept. So I'm going to need to substitute into the equation. I think I will continue from this equation. So if 1 over lambda is 0, 0 is equal to work function over hc plus maximum ke over hc. Oh. Okay, don't forget this Emax here, wherever the Emax number is, this is the x-axis, so you don't worry. Y in terms of x, okay, so the x should be there, okay, but I think you notice the hc can cancel away. Beautiful, that's why 0 is my best friend, you guys, you know. So this hc and hc cancel out. So from here, you will get work function is equal to Emax, which is equal to the x-intercept. Hiyo, that's all. I just need to read the x-intercept, correct? So let us go back and read the x-intercept now. Ding, ding, ding. I have extrapolated the line. I can see, oh, it cuts at -4. Do not write -4. It's not a good number. No lie. It's also because that's 10 to the power 6 here, okay? So please include the 10 to the power 6. So don't worry. This one you move, I've forgotten my negative sign. You move this around, you get work function is equal to negative Emax. Okay. All right, so from here, I can just say that work function is equal to negative x-intercept. Okay, because again, this Emax is your x-axis. All right, let's finish up. So then work function is equal to negative bracket -4. Don't forget the prefix times 10 to the power of, okay, I'm going to look at my paper now, 6. 6. I print so small. Why? Okay, don't, I know, wait, it's not power of 6. Guys, this is what happens when you record at 2 a.m. So this, hang on. Give me a sec. I should write this down as if I'm a student. So this one is your Emax when 1 over lambda is 0. So your Emax is equal to -4. Prefix is here. Times 10 to the power -19. Okay, I'm not going to edit this, so you'll be fine. You get the idea. 10 to the power of -19. Negative, positive law, 4 times 10 to the power of -19 joule. You know what made me pause or not? Because this number have to be very small one. It has to be in terms of E volt. But there's still a mistake, remember? This baby here, this 4, can it be 1 SF? 2. Please at least 2 SF. Alright, 2 SF. Okay, second problem. You might be saying, Miss, you know, when I extrapolate my line, I don't get exactly 4. Is there a range? Yes. As long as this Emax reading is between 4 plus minus or -4 bracket plus minus 0.2 times 10 to the power of -19, you are golden. You are Gucci. You're good. Okay? So 3.8, 3.9, 4.0, 4.1, 4.2, all okay. Okay, so that is this part. This part is a bit tricky and a bit anomalous. Normally, we look for y-intercept or we look for the gradient. But now in this case, since they double bind you, and you cannot use the Planck constant because you need to calculate your Planck constant first. So you have to think a bit out of the box and you have to use this technique, letting 1 over lambda be 0. Okay, this part here. And this one will change to which will be the x-intercept. So using the x-intercept. Gradient, y-intercept cannot. X-intercept is your next option. Okay, great. I can't highlight because I don't think they want me to. Look at this rotating wheel. Okay, anyway, we're back, I think. Let me check. Yes, we are. Okay, so by using 1 over lambda is 0. Okay, this one. Alright, so step 2. Now we want to find Planck constant. Can now. There are so many ways to find Planck constant. You could use the y-intercept, but I would rather just keep it a bit clean and tight and use gradient is 1 over hc. So you can tell from this expression, from this part here, gradient is 1 over hc. So I'm going to write this. Gradient m is equal to 1 over hc. Here. So you write this one, you get 1 mark already. So now we got to find the gradient of the line. Okay, so to find the gradient of the line, I am going to have to go and stare at this place and try to find two values. I am going to just use this point, -4, 0, this point here. And I'm going to use this point. What is this point? I think this point here is 4a. So 4.1, 4.15. It looks like half a box to me. So this is 4.15, comma. Okay, this one is exactly at the thick line, 4. Okay, very nice. So I'm going to use this coordinate, the top part here. And I'll use the bottom part here. -4, 0. -4, 0. I know, got prefix, and I will use it later in my gradient calculation. Okay, let's plug that in. Let's go. To find the gradient, I will make it very obvious that I'm using the gradient equation. So I will use the height, which is the y-axis. This will be 4 minus 0. Okay, don't forget the prefix for the y-axis is 10 to the power of 6. This prefix. Okay, and then I will divide by x-axis difference. X-axis difference is 4.15 minus -4.0. Don't forget there's a prefix here, 10 to the -19. Make sure you include all the prefix from the axis. There's a power 6, there's a power -19. Okay, beautiful. I got the gradient. This is 3 marks. I gotta make sure I show the gradient properly. Even nicer, I will draw the triangle lah. You draw also lor. You have ruler. I don't have. This one is a test of my sanity on the tablet. But if you have a ruler, you can draw a pretty nice right angle triangle. Okay. So from here, this is 1 over Planck constant times the speed of light. So this one you can use times 10 to the power of 8. So now it's time to find h. Let's go. I think I'm just going to find the gradient first to help my examiner. I don't know. In case there's a range of gradient I need to have to get 1 mark. So I'm going to just plug that in. This will be 8.15. 15 e -19. So from here I got my gradient as 9.0797. So I guess this would be 4.90797. I guess 4.908. I write extra as F1 because the Planck constant, these kind of numbers, if you change a bit, then a lot of other things will change. Okay, so this will be, don't forget your prefix, I nearly forgotten, times 10 to the power of 24. Okay, and then this will be 1 over hc times 10 to the power of 8. So from here, I guess we can find the Planck constant. We're just going to take 1 divided by answer, and then divide by 3 times 10 to the power 8. Ta-da! So this one, I got 6.79. I'm just going to round it to 2SF, okay? So this would be 6.8 times 10 to the power of negative 34. Okay, you might be thinking, Miss, the actual value is 6.64 leh. Experimental value ma. Maybe they got some rounding error, some uncertainties, limitations, okay? But this is close enough. The most important thing is the prefix. So if you didn't convert your units in your gradient, confirm the prefix is wrong one. So in front of the number, as long as you get 6 point something, you are Gucci. You're good. But this one must get negative 34 because the actual theoretical reading is 6.64 times 10 to the power of negative 34. 6.64, 6.63, sorry, 6.63 times 10 to the power of negative 34. So as long you must have this negative 34. If not, no dice, bro. Cannot. We need this negative 34 here. This one. Okay, so this is the theoretical answer. Where are the marks, you ask? 1 mark is when you use gradient to find the answer. Okay, the other, this one is actually 2 marks. Is it 2 marks? No, this is 1. Sorry, my bad. This is 1 mark. And then you find the gradient and you show the correct substitution is 1 mark. All right. So the range that they accept, acceptable range, is 6.6 to 6.9 times 10 to the power of negative 34. So like I said, this number is not that important. It is the prefix that will cue you in, that will let you know. Cue, give you the cue or the sign or the clue that your prefixes, you didn't convert some units or you didn't copy a prefix from the graph. Okay, so this graph is a little bit special. It's not like the normal Emax or Emax against frequency. They go and put the Emax on the x-axis. So the calculation here will look a bit sus one. So the moral of the story here is you should not memorize that, oh, if the graph is like this, the gradient must be this and the y-intercept must be this. Because I can easily change any of these axes, any of this fraction. The ability to linearize your equation you also need to use in your paper 5 is so important for your A2. Okay, so you can try different technique, but from here I can see gradient cannot use because got Planck constant. Y-intercept cannot use because got Planck constant. So I got to be a bit creative and find the x-intercept. All right, and then this part is just pretty standard. Okay, so that's it for this example. If you find this helpful, as usual, share it with friends, enemies, neighbors, share it with your buddy, your dog. Maybe they'll like to watch me. I don't know. Are my jokes lame enough? Okay, anyway, I will see you in the next video. Comment, chat, let me know what you think. Okay now, bye-bye.